Hello friends, welcome to the today's session. Today our agenda is how we can able to do parallelization. So parallelization can be achieved only through either creation of the children using a fork or running the process or split the process into smaller parts known as threads. So we will discuss how the fork and thread are going to implement on multiprocessor architectures. That means whenever a system has more than one processor, how we could able to run the parallelization with the help of fork and threads. Before going into the lecture, let us see our anthem, Crack GATE and ESE with India's largest learning platform, none other than Unacademy. Get Plus subscription and access unlimited live and recorded courses from India's best educators. About myself, Srinivasarao Sir, having 17 years of GATE experience with a high success rate and taught in many premium academies including GATE Forum, the GATE Academy and MADESE too. Throughout my journey of GATE, many of students are qualified into IITs and NITs and completed their graduation, and some of my students also completed their post graduations and doctorates. Now it is a chance to current ongoing students, those who are writing 2021 or 2022 GATE examination. So get the subscription using my referral code Sankara to get the 10% off, because once you get the admission, then you're going to get complete pack of the lectures of different educators and different kinds of mock examinations you're going to get benefited. So utilize this opportunity and utilize the complete pack of courses and lectures and get admission into IITs and NITs. So third year students and second year students can prefer 24-month subscription where you people are having ample time so that you can able to have n number of recaps. So this is the schedule which we are going to follow in the upcoming month on the subjects of operating system. So those who not yet take admission in an academy, immediately take the admission using my referral code, because very soon I'm going to start another subject on plus. So these plus courses are not available to the non-subscriber students. Now let's crack GATE CSC. Hit the bell icon for the latest notifications. Subscribe to YouTube channel, Unacademy's YouTube channel, that is Let's Crack GATE CSC. So let us start today's topic, that is we will start with fork, how the fork is going to provide parallelization. So when I'm talking or when somebody asks you what is a parallelization, now you can say very easily that running the multiple process on multiple CPUs. That's what we seen in the last session, that how you could able to run the multiple process on multiple processors. So instead of running the processes, and what is the reason behind that? The reason behind that is parallelization can be done with the help of fork and threads. So fork is playing a very important role in order to create the children of a particular process, and that you can able to allocate to a different processors. So how it is to be done, we will look at in this session. So when you talk about a fork is a system call, you can say it is a system call which is used to create children process. That's nothing but child process. So if a single process would like to split into multiple process, that's possible with a fork. but the different aspect of the fork is nothing but the fork is, instead of creating a separate sub-processors, it is going to create a same process once again in the form of a child. Now you talk and we say that it is a system call which is used to create child processes. So what is a child process? A child process is a replica of your parent process. Whatever the instructions are there in parent process, the same instructions also are there in child process. You can also say that this is a concept called mirroring. What is the meaning of mirroring is, so you will get one more kind of same process in order to execute onto multiple processors. So here what is going to happen? So what the fork is going to tell you, just by creating children processes, the fork is saying that you can able to achieve the parallelization. So parallelization can be achieved using this because the parent and children can able to run onto multiple processes. Therefore, and one more thing is that the fork does not have any kind of parameters. It's a one kind of a function. This is also called as a fork, is also called as a system call. A system call is nothing but it is going to give some kind of interrupt to the operating system that some other process is going to be created, because the nature of the fork is nothing but creation of the child process. Now you observe, once after child is created successfully, then how come you know that the child got successfully created? So there is a reason and there is a hint. What is that? If a child process is got successfully completed, then the fork, the system call, is going to return few values. What are the values? So if at all the child process creation is successful, it returns values, two different values to one value it will give to parent process and the other value it will give to child process. So what are those values? The fork returns a negative value if the child process creation is unsuccessful. So you will get a negative value in the case of what the child process got created not properly. Therefore, you will say that if child process created is unsuccess, then you can understand that the child is not created. If at all the child is created, and two important points you can understand that it returns a zero value to a newly created child process. So here you're going to get a value is what? Zero in this. And it is going to give you positive value to your parent process. These two values you are going to get only in the event that is a what? If at all the child process creation is a what? Successful. So when the child process creation is a successful, then you will understand that you are going to get two values, one value to parent and one value to child. The child will get a value called 0 and the parent is going to get a value called greater than 0. That means the parent, whatever the value it has got, that value is nothing but the process ID of the particular child process only. That's why whenever you get a process ID, the process ID value is greater than 0. That's why parent has got the greater than 0 value, which is nothing but the process ID of the child process. And the child itself confirms that if the child receives the value 0, it comes to know that the child process creates successful. Otherwise, it returns a negative value. The negative value will say that the child process is got failure. Now, this is about the fork, and what else the fork will tell you. Once the child process created successful, the parent process and child process exact replicas only. So the child is having the same copy once again, however, the parent has got. And another important thing is that the parent and child will be executed from the next instruction after the fork statement. This is very much important. Whenever fork statement is being called for, and the next time when the both parent and child are get to be executed, they get to be executed from the next instruction only. This is important point. So therefore, you understand carefully this point. What is that? After the fork is called for, if at all it is successful, then parent and child process executes from next instruction. So this is a very important point. So therefore you will come to know that how the child and the parent process are going to be executed from what particular statement. So they are going to be get executed from the next line only. So we know the child process is exact copy of your parent process. Here there is a concept of address sharing. What is the address sharing? Whenever you create a child process onto your parent process, please observe carefully. So whenever the child is created onto your parent process, there is a concept of address sharing. So when you talk about the address sharing here, so what is the address to be shared and what is the address not to be shared? So this is a very important point. What is that? A logical address is shared by child process, and you say that the logical address is same as like your parent process. But the physical address can be anything for parent and child process because they are not going to share the physical address. They are to be sharing only the logical address. Logical address is nothing but what? Your what? Logical address is nothing but what? Your CPU generated address that is going to be shared by your parent and child process. It's nothing but this address sharing is nothing but what? A logical address which is belongs to your hard disk, you can say. Otherwise you can simply denominate as secondary memory. So this is going to be shared, but physical address is going to be not to be shared. This is another very important point. Therefore you will get different physical addresses from your parent to child process. So how this to be created? I will show you one example. Observe carefully. Now, if I'm calling an example like this example is telling you that there is a main statement and there are two forks are there and we are trying to print an academy. Now here what is going to happen? As soon as you run this program, after running, please understand friends, after running, what is going to happen? It's first of all executes your main. This is your first statement, and the second statement is a delimiter, and third statement is a fourth, and another statement is also fourth, and finally it is going to print an academy here. So how this is to be done? I will show you. Observe carefully. I'm talking about a parent now because the currently running process is nothing but your parent only. So I'm saying, for example, this is a welcome.c. If I am designate a name welcome.c, your parent is nothing but welcome.c only. So it start executed, statement 1 is executed, statement 2 also executed. Soon after it comes to 4, then what is going to happen? It is try to create a one child process. So as soon as it create a child process, I said that the child process is exact replica of your parent process only. Therefore, what is going to happen? You see that you will get here whatever the statements are there in your main program, that is a parent program. So main and open delimiter and fork statement, and next one is a fork statement, and next one is a printf statement and bracket close. Whenever you call this for, then what is going to happen? You will get one more main here and fork here and fork here, then printf statement here and bracket close. So I said that. So the parent has got completed these three lines. And the same are applicable to child also. What child is going to do? The process child and parent are got to be executed from the next line. What is your next line? Here also three lines are completed and it is come to know that this is the line I need to execute, which is going to be entered into your program counter, and this. So this is already completed, so this has to be executed this line. Therefore what happened? Next instruction to be executed is after the fork this one, and after this fork this one. Then what is going to happen? This fork, when you call, it is going to create a one more child here. Please understand carefully. It is created one more child here because of this fork, and which consists of same main here and a fork statement and a fork statement and a printf statement and bracket close. So now after completion of this parent, you see that this parent and the child is going to be executed from this line, because already we know that the second fork is also got to be completed. The instruction is going to be executed from the next line from parent as well as the corresponding a child. What is the corresponding a child here? C2. The C2 is created from this and C1 is created from this. Therefore, the next parent comes to the next line. It prints a hello here. Please understand, as it is completed two forks. And but once you come to child 2, so child 2 will get to be executed after the second fork. This is the line it is going to be executed. It is also going to be printed a statement called hello, because we know that after fourth statement, the fifth statement is been handing over to your child and to the corresponding parent. Then you will get a hello here and you will get a hello here. Now you observe, this child is not yet fully completed, just it is being created only. So this has to be executed from this particular line. As soon as you create this 4, then what is going to happen? It is going to create one more process now, and this process is created because of this. So which consists of a main here and here f here and f here, then finally printf statement and closing delimiter. So soon after completion of this particular child, this parent, now C3 parent is a C1 this time. C3 is the child to C1. Please understand. C2 is the child to your this parent, and this C1 is a child to this parent. So this parent program has got two subchild C1 and C2, and C3 is not a direct child to the original parent. C3 is a child to C1 only. So soon after C1 is being called for second fork statement, then it is executed, the next line to be executed, and because they are executed fourth statement and fifth statement is a line there, and so we got print here hello and hello. So finally we understand that your Unacademy is going to print a four times. So Unacademy is being called for 4 times, and you know that total processor, you will ask in exam this question only. Total processes are 4, in that 3 are child and 1 is a what? Parent. This is important. So 3 child processes and 1 is a parent process. Now how can you run this? So I am running onto multiprocessor system. You assume that I have got 4 processors. Let me take, let 4 CPUs are there. Please understand friends. In that 4 CPUs, we got CPU 1, and we know that this is a CPU 2, and we know CPU 3, and we know CPU 4. I am using a symmetric concept, symmetric operating system. Therefore, what is going to happen? Every CPU is responsible to run one kind of process. Either it may be a parent process or it may be a child process. Now you observe carefully. Here, if I am giving your parent process 1 and child 1 will be executed here, child 2 is executed here, child 3 will execute here, all are trying to share your memory. This is the concept of inter-process communication. Now this memory is under sharing among all your CPUs. 4 CPUs, but only one memory is available. That's why this memory is being designated your process into at different address locations. They will not be available at the same address locations. That's why physical address is going to be given different, but logical address is going to be shared, because this program is belongs to either particular C drive or D drive or some particular location, and the childs are being placed onto different processors. Hence logical address is the same, but physical address is going to be the different. Now you observe carefully friends, 4 processes at a time, they had to be executed. Finally we are going to get 4 different outputs, but if they are not different outputs, they are having a same statement. That is a what? Unacademy we are calling. So you will get an academy statement here, you will get an academy statement here, you will get an academy here, you will get an academy here. What is the advantage? The advantage is nothing but you're going to get multiple different outputs from different processors, but you see that ultimately their output is the same. So what do we understand? Advantage is that utilization of multiple processors. Utilization of multiple processors. But what is the disadvantage? This is a very poor. What is the poor? All the CPUs are going to generate what? Same output. What is the use? No use. No use, because every CPU is going to generate same output. Why should we require? But sometime it is very much required. Why very much required? I want to see that instead of a for loop, please observe, I will give an analogy. You people may be having a doubt that why do we use a fork statement? Because output on from all the programs are same. Yes, I do agree. But in what cases this fork is very much useful? You observe carefully. For example, yeah, please understand. For example, I'm saying as like this, there is a main program which we are having int I. I'm starting I is equal to 1 and there a loop I is equal to 1 and I less than something like 10 lakh and I plus plus. So I'm going to call printf I. So I want to get this output 4 times. That's what my motto. 4 times we want to see output. Please understand, friends. 4 times you want to see this output on screen or printer, whatever it may be. On screen or printer, whatever it may be. So how are you going to get this? It's not possible. You will get only one time only. Please understand, friends. All of you, those who are on live, understand carefully. So you see that I want to generate the same 1 to 10 lakh numbers. I want to see 4 times. So how it is possible? It's not possible with a single process. It's not possible with a single process because your single process can give you only one time of 1 to 10 lakh numbers. Then how can you generate 4 times? I need to write 4 times 4 loops. Yes or no? So this is the first for loop. And I am going to write the same in the same program. Second for loop I will write. In the same program I will write third for loop. In the same program I will write fourth for loop. Therefore, what is going to happen? Your main consists of 4 for loops, and each for loop is meant for to generate a 1 to 10 lakh numbers. Okay, we can survive in that concept. So what is going to happen? You are trying to increase the complexity in the same program. What is the complexity? You observe that to repeat this loop from 1 to 10 lakh, you please try on your system, you will come to know what is the problem. There is a problem. So if you run one loop for 1 to 10 lakh, then it is going to take a much time to display output on your screen. So one time it takes a lot of complexity, and a second for loop to give you 1 to 1 lakh, 10 lakh numbers, again it is taking so much complexity, and the third time again so much complexity, and fourth time also so much complexity. So what do we know? We want to do a smart work here. What is the smart work here? Instead of writing a redundant code, please understand, I am telling you, instead of writing a redundant code n number of times, better you utilize the concept of multiprocessing structure. What is a multiprocessor structure? Instead of writing 4 loops, simply I will use a concept of 2 forks, and these 2 forks are responsible to place your particular program onto different CPUs. So when this is going to be very useful, please understand. If I am having CPU 1 and CPU 2 and CPU 3 and CPU 4, either it may be physical CPU or it may be logical CPU, no doubt. So what is going to happen? If I call fork statements instead of 4 for loops, so simply you say that this is a 1 fork and this is a 1 fork. When you call for, then you're going to get one processor here. This is a process 1, this is a process 2, and this is the process 3, and this is a process 4. So your work will be completed 4 times output. You will get only one instance of time. Please understand, at one instance of time you could able to complete the 4 different types of what I mean to say output instances. This you can able to see on a sharing of a printer concept. What is the sharing of the printer concept? If I give a print, I want to get the 10 different printers, 10 different printouts. How this is possible? Yes, this is possible using a concept of what? 4. So as soon as you give the click print, then the 10 printers are going to be responded and will give you 10 printouts. Manually it is very much difficult. So why? Because we are having the concept of what? Different CPUs. If you are having, then better use a fork statement. If you are not having a multiple CPUs, then you cannot use a fork and thread concept. Again, friends, I am telling you this particular fork and thread concept only whenever you have the concept of what? Multiple processors. When you have the multiple processors, then you go for fork and thread. If at all you have a single processor concept, then there is no concept of what? Fork and thread. Because fork and thread are going to create a sub process either in the form of a children or either in the form of splitting of your process. Now what do we understand? In these cases, we want to see that the fork is very much useful. So what is the advantage of fork? Please see, friends, the advantage of fork is nothing but multiple instances, multiple output instances at the same time. This is one of the best. That means what? You will get a more throughput within a single amount of time. If you are having a single processor, I am not using other processors, I am giving only complexity to the program. When other processors are idle, then your time complexity of the program is being increased in order to generate the multiple output instances. So better use all your multiprocessor architecture just by creating a child process using the concept of what? Fork. This is the concept of fork. Why do we require a fork? And what the fork is going to do. I hope so you got cleared. So one of the audience is asking a question like this. So whenever there is a parent process is there, if that parent is created as some child here C1 and C2, now you see that this child also can able to create another child. No problem. This child also can able to create another child. Now in that case, this is a child to this and this is a child to this, but overall they are coming from only one parent only. But this is acting as a child as well as process. This is acting as a child as well as process. Sometime it is acting as a child, sometime they are acting as a what? Parent. Because parent to the down layered process and child to your original process. Okay, so come to next point. So how can you write the program for your fork? Very simple. I say main statement and it is going to return what? Integer value. That's very important. What fork is going to do? Fork is going to do either positive value or fork is going to do zero value or fork is going to do negative value. They all belongs to integer only. So I am taking a one variable called PID and I have assigned this fork into this PID. Observe carefully, friends. As soon as you assigned this fork into this PID, if fork success, then we know. If child process got success, we know that it is going to create a positive value and it is going to create a zero value. If the fork got failed, then what do we understand? It is going to give you negative value to that process, whichever it is calling your fork statement. Now here that's what the program we are writing. What is that? If PID is less than 0, less than 0 is nothing but negative value, you can say that the child process got created failed. If you get positive value, then we can understand this is for positive value. This value is assigned to your parent process. If at all you got a 0 value, then we can say that the child process got created successfully. These two conditions only when child got created successfully. When child created successfully, then you will get the two values like this. then only you're going to get zero value as well as a positive value. Okay, friends. Now let us see. I want to show you how this is going to be done. I'm saying this is your welcome.c. Now I called like this. There is a main, and I am saying fork statement and bracket close. And there is a printf statement, welcome. Observe, friends. As soon as you run this, after running, what is going to happen? It just called a main function, so no action, it's done. And the second statement also got executed. As soon as it call fork, and what is going to happen? We know it is a system call without having any arguments. Immediately take you to execute another process on another CPU. You execute that. I am running this on CPU 1. Immediately it will push you onto CPU 2. That's what the meaning of or nature of your system call fork. And you will get here once again same program, that you will get a main here and you will get a fork statement here. You have got a printf statement there, same replica. Once again you will get welcome statement here and bracket close. Here also you got printf and welcome statement you have got. Now you see how come it knows that, for example, if I am keeping this program name is welcome child. Now how come this program knows that welcome.c knows that it is my child? This is very important. Now you understand this welcome child is belongs to which parent process. That's very important. There is a requirement of proper binding. Otherwise there will be ambiguity that this child processor belongs to which of the parent process. So this ambiguity can be eliminated using the concept of returning the two values. One value 0, one value to your positive value. So now you see that every process is going to give one process ID. Please observe my original parent program. If I am taking my original parent program process ID, if I am taking as 100, this is my original parent ID, process ID, that is 100. As soon as this is success, if at all the probe key is got created successfully, it is been designated to CPU 2 because my original parent program is running on CPU 1, and it is also get to be given a process ID. Please don't forget that. Every child processor, every parent processor, every process is going to give a process number. So I'm going to get, for example, process number I got 200. Now what will happen? This 200 you will get only when the child got successfully only. This 200 will pass to this parent process. Now I will come to know that the particular process ID 200 is one of my child and not to anybody else. Otherwise this child will come to know that process ID is equal to 100 is my parent, not somebody else. So this kind of a proper binding is required between exact parent and exact child process, just passing your child value process ID, child process ID to your parent process. Now your parent process has got two values. One value, its process number, that is 100, and another value it got received, that is nothing but 200. So it comes to know that 200 is my child program, and it comes to know that 100 is my original process ID number. So this is how you come to know that both are linking each other. Otherwise there will be a good ambiguity which child is belongs to which parent process. So to avoid that ambiguity, the fork is going to give you two values in the event of success. One value, the child process is going to get 0, and a positive value, that means what, the child process number is going to be handed over to your parent process to say that I am one of your child. So in order to do this, this small program is helpful in order to create successfully our child values. So what do we understand finally? Let me give you a one flow diagram so that you will better understand. What is this flow diagram? I say my process ID is 100. I got executed main, then delimiter, then I call fork statement. As soon as you call fork statement, the parent process is going to be get executed from next line. Please don't forget that. So now this fork will tell you two cases. If you are failed, what is the value you are going to get? If you are failed, and this is going to give a negative value to the calling function. Don't forget that. If it is a success, please understand friends, if it is a success, it has got created one child process and it is going to give a child number. As we guess that, let us take 200, which consists of same replica once again, main here and fork statement here, and I am saying a printf once again a same line, that is hi and bracket close. Then not only uh, doing this kind of successful creation, this will give you 0 to this process. So the fork is going to give 0 to, please understand, the fork is going to give 0 to your child process, and this process ID, whatever is allocated by your operating system, that will be passed to your parent process. So parent process comes to know that, okay, my child got created successfully, and child also comes to know that, okay, I have got created successfully by somebody else. So now you see, after creation of this fork statement, the next line they get to be executed is a HI here and HI here. And finally, we understand that your output is being executed at two different processors, HI and HI you're going to get. If I am assuming that this is running at one processor and this is running at another processor, both processors are busy in executing and you will get the same instance of output, same output from different CPUs. So my motto is satisfied. What is that? I want to execute multiple instances of output on multiple processors because I am using a multiprocessor structure, and that too I want to reduce the time in order to get the multiple same outputs. So this you can able to achieve with the help of fork statement. So let me give you a one flow diagram how the childs are being created. You will understand. Now you see, this is your parent process, so which consists of, as usually, main here and fork statement and fork statement. When you run this, after running, so what is going to happen? First fork is called. Whenever first fork is executed, when I am executing first fork, what will happen? It parallelly run your parent process. Observe friends carefully. It parallelly run your parent process. It also parallelly run your child process. This is your child process. Observe carefully. Both are running parallelly. Don't forget that. This is your parent. This is your child. Understand? Now, as soon as you create one more time your fork statement, what will happen? This parent, once again, it is carry forwarding as a parallel, and this is get to be created one child process here, and this child as usually carries as your parent process, and this child further creates what? Another child process. Now you observe, you see that this is your main parent program. This is the main your parent program. You understand that this is your main parent which is running concurrently. Other three processes are your child process. This is child 2 and this is your child 3. This is your parent and this is your parent. You understand that parent is running parallelly and child is running what? Parallelly onto other process. So we can understand using that what we see total processes are 2 power n. Total processes are 2 power n, where n is nothing but number of forks. Observe carefully. And how many childs you can say? So you can formalize as like this. The number of childs are nothing but total processes minus your one of your parent. So I can write like the 2 power n minus 1. So total processes minus your parent process is a concept of your number of child. So I can write here your number of child processes are total processes minus parent. So don't say that there are three parents are there minus parent process. So 4 minus 1 you will understand that three child processes you will get. Okay friends, so this is the flow. What is the flow? For the first fork, this is your first fork, and the second fork I am calling in next level here. So second fork, as soon as I call here fork statement, then if the parent runs parallelly, it creates a child. This process run parallelly, this creates a child. So three child process and one parent process. Okay. What is the drawback? What is the disadvantage? The disadvantage is like this. So unable to utilize multiple processors effectively. This is the point why we are going to get a what duplicate output. So duplicity is one of the problem. Duplicity output. We are making run all the machines, but what is the use? The use is nothing but same product is coming. This is the disadvantage, but this is also advantage. What is the advantage? You want to get the same product from multiple machines, then you can use the concept of fork. But disadvantage is that I don't want to generate the duplicity. I want to generate a unique output, but it is not possible to generate unique output because every process is going to get generate only same output only. Okay. Now please don't forget to this particular point. What is the point is, as soon as you call the fork statement, so this is the finishing touch to your fork. As soon as I call the fork statement, then next time the program counter starts to execute from next line. Please don't forget that. This is applicable to your parent process as well as it is applicable to your child process. And what is the meaning of that? Once soon after you call the fork statement, the parent process and the child process will be executed from next instruction what the program counter is storing. So the next instruction onwards, it is going to be executed its particular program, not from starting. That's very, very important. If you see that it is going to create from starting, for example, I called a fork statement here. You see the child is created, it is executed one more time, then it is going to create many children. It is ridiculous. So please understand my important point. What is that? Soon after the fork statement is called, the parent and the child will be executed from next instruction, not from the same instruction. Okay. And now what we want to do? We want to have a different tendency. What is that? I have got different CPUs like this. I want to run the program and I want to see that unique output on the different machines, not the same output. So you want to get the different outputs of your same program, then it's not possible with a fork because it is also going to concept of what your main memory is under sharing among the different CPUs like this. And what is going to happen? Different CPUs has to produce a different output. What is the meaning of that? I want to see that this is going to give one output 1 and I want to see that this is going to give output 2 and I want to see that this is going to give different output and this is going to give different output. You want to generate different output and I want to see that all the sub processes are running on different CPUs. So you can able to achieve the parallelization not only from fork, and fork is going to give you that to duplicity. I want to use that same objective, I want to get that with different output, then I have to use the concept called what? Threads. So what the thread is going to do? Thread is very similar to fork, but instead of doing duplicity, it is going to give you a different unique outputs. because every thread is nothing but what? A smaller unit of code only. So how threads are going to be executed, I will show you, and how they are being created. Let us see. Now you observe, when I am saying a thread concept, then what is going to happen? This is your parent process. This is your parent process. Now this parent process is split into, please understand, they are not sub-created, is split into smaller sub-process, part of parent process. This is also part of parent process. This is also part of parent process. And this is also part of parent process. So what do we understand? They are not different core processors. They are what? Sub process of your parent process only. In fork, what will happen? You see that same piece of code is going to be executed there and here. So that if parent program size is 100 MB and all the child process size is also 100 MB only. Don't forget that. But here it is not like that. If I am saying that my parent program size is 100 MB, I can able to split into 4 threads. Then what is going to happen? Each thread is only capable to run a maximum of 25 MB only. So this is running 25 MB and this is running 25 MB piece of code. This is running 25 MB piece of code. This is running 25 MB piece of code, and I am giving to different CPUs. So my motto is achieved. What is that? On multiple CPUs, the program is going to be executed, but not the full program. It's only part of the program. Then what is going to happen? The time complexity is drastically reduced. If you run a single program on a single mission and the same program I am doing on to different mission, therefore your total time is being divided into 4. So within a quarter time, you could able to complete your total program using the concept of what? Executing a piece of code, not the complete code. So executing a piece of code is a concept of what? Part of a process. A part of a process is called a sub process. It's called as what? Thread. So threads are playing a very important role in order to achieve the what? Parallelization. Thread is called as a quasi-parallel. What is the meaning of quasi-parallel? You can able to execute the sub-process onto multiple CPUs, not the total program, only part of the program only. Or where these threads are going to be utilized. Let me show you. If I am saying my program is like this, so this is my main program, which consists of almost all 1 lakh lines of code. 1 lakh lines of code. So if I execute this, if we execute this program, please understand friends, how real-time the threads are very much useful. If we execute this program, then it takes much time. So what I want to do, if you are having multiple CPUs concept, CPU 1 and CPU 2, I have CPU 3 and I have CPU 4. If I run this particular program, then what is going to happen? Your program is get to be executed only at one CPU, either CPU 1 or CPU 2 or CPU 3 or CPU 4, because altogether you are executing a single process only. So if you go for fork, what will happen? All CPUs are busy. Please understand, all CPUs are busy. Our motto is satisfied, they are not idle, but what is the use? All CPUs are taking the same time by running a 1 lakh lines of code only. So what is the use? No use, because all are getting same output only. So what do we want to do? We want to do cleverly. What is that? This 1 lakh lines of piece of code will be divided into 4 parts, as I am having a 4 CPUs. Therefore, what happened? 1, 2, your 25,000 lines of code will be executed at CPU 1, and next 25,000 lines of code will be executed at CPU 2, and next 25,000 lines of code will be executed at CPU 3, and next 25,000 lines of code will be executed at a CPU 4. So exactly at a quarter time, all CPUs completed their task, then your output is going to be displayed. Your output is displayed only at a quarter time only. So this is the concept of what? Threads. So how are you going to do this kind of splitting? So this splitting can be done using three important tasks. What are the three important tasks? Observe carefully. Now if I am saying thread has got mainly few system calls. What are that? Thread underscore create. It is going to create a threads. Next one, thread underscore join. What is the meaning of a join? Because they are executed in a small processes, nothing but threads only. Thread 1 and thread 2 and thread 3 and thread 4. They have to be joined later because as soon as I created and you're going to get a four threads like this. Thread 1 first 25,000 line, thread 2 next 20,000, next 25,000, thread 4 next 25,000. So I need to join them. How are you going to join them? You can join them using a system called thread underscore join. Once after output is printed, after output after, threads are going to be destroyed. So you need to use the concept of what? Threads underscore destroy. You want to sleep any of your thread, you can use the concept of what? Sleep system call, so that one thread or two threads can be what? Sleep. So these are the main system calls: creation and join and destroy and sleeping, and one more, blocking. If at all they are going to fall into deadlock, and those threads are going to be what? Blocks. So this is what is the meaning of a block system call. So using the system calls of your threads, and your thread is going to be executed. So what is your thread now? Let us see. So your thread is nothing but it's a part of the process only. So you see that a process is a group of resources, but thread is having only part of the resources which are executed onto different CPUs. So thread is called as a what? Quasi parallel, and thread can run only one at a time. Thread executes sequentially one after another, and the thread creates a separate stream of execution within a process, and these threads are not isolated from each other. Every thread is going to be communicated with each other. If any thread is going to give a block system call, then entire process or all threads are going to be blocked. That's why threads are being communicated each other from one particular CPU to other particular CPU. So who is going to do? So the operating system, with the help of thread control block, please understand, as we are having a process control block in processes, here we have a concept called as what? Thread control block. So thread control block is very similar to process control block, which is trying to store the information about your thread. What is the thread ID? What is the thread state? What is the thread priority? What are the list of registers you have used? What are the sequence of files you have used? That information is loaded into your thread control block. So thread is also having a priority, high priority threads or low priority threads. Thread is also having whether you are in running state or sleeping state or blocking state. So that information you will see in thread control block. And thread independently executes on each other, as we know that threads created and managed and controlled by thread control block. This is an idea. So there are two kinds of threads execution. One kind of threads are called kernel level threads, and one kind of threads are called user level threads. So whenever you call kernel level threads, they will be executed in kernel mode only. Whenever you say the user level threads, they are going to be executed at user mode only. So both processes, both different threads are having a different kinds of mode of execution. Here also you have the concept of process status word or thread status word. Either it is going to tell you that what kind of a thread it is, whether it is operating system thread or a normal user thread. What is the other important thing? So this is the important point. What is that? Thread can use the concept of fork statement. It can create the children, and you say that each thread has got resources, separate resources or restricted resources, And the threads are mainly for what? Sharing of the resources. What it can share? It can share CPU, it can share address space, it can share code, it can share data, it can share files, whatnot. Everything can be shared, but three cannot be shared. What is that? Stack. Every thread has got its own stack. Every thread has got its own registers, because stack will tell you that any kind of, what I mean to say, runtime environment that is going to be located in a stack. And registers mainly tell you that the context switching among the threads is done by your registers. And program counter, what instruction to be executed if at all you are suspending from other threads. So that's why these three are important. What are important? Every thread has a stack for local variables and recursive functions, and every thread has got what? Registers. And every thread also has got what? Program counter. But the threads are going to be under sharing. What it can share? What it can share? It can share code, it can share files, it can share data, it can also share what? Heap, it can also share what? Global variables, because the global variables we are going to keep in heap only. So these are going to be under shared, but they are having a dedicated three important components: stack space and registers and program counter. These are the three important things you're supposed to maintain. Okay, so the OS maintains virtual memory for every thread. So virtual memory, whenever you are calling, they are going to be executed on a concept of what? On demand concept. So thread shares what? Address space. And now see, what are the advantages of threads? The advantages of threads are like this. So these are the advantages of threads. What are the advantages of threads? You see, so responsiveness, very fast responsiveness. Very why it is very fast responsiveness? Because the thread is nothing but part of process. So instead of executing complete process, what we are doing? We are doing only execute only half part of the process only, or quarter part of the process. When you are executing quarter part of the process, then responsiveness is very much decreased. That means what? Increased. And you will have that context switchings. What is the context switching? A thread is a word. Please understand. Thread context switching time is very lesser than your process context switching time, because the process is a what? Heavy weight. Please understand, process is a what? Heavy weight, and the thread is a what? Lightweight. Why it is a lightweight? Because I am not carry forwarding anything. I am sharing a data myself, I am sharing a code myself, I am sharing global variables, I am sharing address space, so I am not having anything. I am having only very small part of code, which including what? Your stack and program counter and registers remaining all are under sharing only. That's why thread is called what? A lightweight process. But process is a full heavyweight process, because you need to maintain all the kind of stuff, because the process are independent, but threads are what? Dependent, which is under sharing mode. So that's why it is called as what? Resource sharing. What kind of resources you can share? Heap you can share, global variables you can share, address space you can share, and what else you can share? Data you can share, files you can share, code also you can share. It is under completely the sharing of the resources only. So throughput can be executed and increased. Why throughput can be increased? So at a quarter time I could able to complete your process. If I am executing entire process, it takes a lot of time, because I am taking only quarter time, so that I could able to complete the entire process, because of using a what? Multiprocessor structure. And effective communication between entities. Entities are nothing but threads. That means each thread will communicate with the other thread. So intercommunication of the threads is happening with the help of inter-process communications like this. So effective utilization of multiprocessor system, because it is going to give you what? Unique output, not the redundant output. And it is economical. It's not that much expensive as like your process. Yeah, there are three components which are not going to be under shared. Please observe, look at this structure. You will come to know. This is your thread structure. What is a thread structure? So I am following this a single thread. Observe carefully. This single thread is under sharing mode. Your data can be shared, files can be shared, code can be shared, global variables can be shared, heap can be shared. So what you cannot share? Register you need to maintain carefully. Counter you need to maintain carefully. Stack you need to maintain carefully. Those three are the components you're supposed to use dedicatedly for every thread. If I'm having multi-threading concept like this, there are three threads are there. All threads under sharing mode only. Code can be shared, data can be shared, files can be shared, and what else? Heap can be shared, and what else? Global variables can be shared, and what else? Code can be shared. But you see that every thread is supposed to have registers, counters, and stack. This thread is also required register, counter, stack, and this thread is also required what? These are the things. And you know that all these threads are being under the control of what? Thread control block. When I am creating a thread 1, then which is associated what? TCB. This thread control block along with your PCB process control block is also being controlled and managed. That means your TCB is being pinned. Your TCB is being pinned along with your thread to the ready queue, because I need to observe that every time what is the state of the thread, whether I am in a blocking state or I am in a runnable state. So that information is being informing by your TCB. Now come to other one. So what is the other one? Threads are dependent on process. This is important. They are not independent. And what is other important point? Registers mainly they are involved in context switching of one thread to other thread. Why there is a requirement of context switching? You may have a doubt. For example, you say one thread 1 and another thread 2. Please see that this thread 2 is under running, and this thread 1 has got a higher priority, and this thread 2 has got a low priority. Therefore what is going to happen? This thread immediately occupy onto this particular CPU, and this thread 2 will come back into your ready queue. Therefore what is going to happen? There is a concept of a context switching is happening, saving the context of a thread 2, loading the context of a thread 1. That is done in this case a concept of what? Registers. The registers are mainly starting and stopping of your threads. So any doubts, please respond through comments so that I can discuss. So what are the differences between your thread and process? So this is a very important 1 mark questions. The difference between thread and process. In the evening special class we will do the questionnaire on these threads and fork statements. Don't miss that evening class. So what is a process? Let us see first of all some important characteristic of the process. What are the important characteristics of the process? Number 1, every process is associated with PCB, and the process is independent. And the process got what? All the things, stack I need, registers I need, and program counter I need, and individual code I need, individual data I need, individual what? Files I need. They are not under shareable mode. Process is under non-shareable, but thread is under shareable. There is no concept of resource sharing in process, but there is a resource sharing in threads. And if at all process dies, then all its threads also will die. But if at all its thread is die, its allocated stack only will be collected. Remaining threads are as usually be running. If any thread issues a block system call, then all the threads are going to be blocked, but the process is not going to be blocked. So these are the important differences between your process and threads, as a thread is dependent on your process. So what is the first important point? Every process has got all the things. What does that? Code required, data required, files required, heap required, stack required, registers required, and every process execute on its own address space. But threads are going to be under executed on parent's address space only, because address space is also going to be shared here. And next point is process is independent. And next point is every process, if I am using a thread concept, every process is a one thread. So when I am saying a one process, I am executing a concept of what? One thread only. So threads within the process can share code, file, data, and as well as global variables, as well as heap. And next point, if process thrives, then all the threads which are being created on the process will automatically dies. That's very important. If any process is killed, then automatically its threads are going to be killed, because threads are depending on your parent. And there is a requirement of what some system calls here And the context switching is more in the process, and context switching is less in the threads. For the let's thread has got no data segment or a no heap, or you can say that no address space, or you can say that whatever that they are under share, it is not going to maintain. A thread has got only what? Three important things what I said earlier. So thread cannot live on its own because it depends on what? Process. So thread can be more than one, and each thread has got three important things. What is that? It is required its stack, it require your program counter, it require its registers. If thread tries, then automatically the allocated memory is going to be reclaimed if at all the thread is died, because whatever the stack is being allocated to that, that stack is being retrieved back once the thread is died. It doesn't require any kind of a system call, a separate system calls. But you don't forget the thread is having a local functions like thread underscore create. I already shown you thread underscore create. It is used to create the threads. Then after creation of the thread, immediately need to make the what? Joining of the threads. And you can go for what? Sleeping of the threads. Sometimes the threads going to be under blocking, and finally, once after completion of your program, the threads are going to be what? Destroying. Don't forget about these important calls. And your context switching time is very less as comparatively to your process. So the next important point is that sharing same copy of code and data is possible, but process has got a different code and process. Please, all these important points only where you cannot remember, where you cannot get from other materials. Please understand, so much of R&D I did to gather these points. So as we know, threads are dependent and processes are independent. Process run in a separate memory space because process need separate memory, separate address space. This is what is the meaning of memory stands for, separate address space, whereas thread is running on in the shared memory space. So whatever the memory the parent has, that memory is going to be shared. And the next one is very important. This is 2-3 times given in the examination. If thread got blocked, if one thread got blocked, then automatically all threads will be blocked. If any one process is got blocked, don't mind, other processes are going to be under execution only. This is very important 2 points. What are that? If any thread of a one particular process is blocked, and the corresponding threads of the same process will be blocked. But whereas in the process, a different process, if at all one process is under block, other process don't mind, they can able to execute on its own, as the process are what? Independent nature. So very fast communication here, and the communication taking a much time here. And thread has got no overhead, but process has got what? Overhead. Here overhead is nothing but I'm talking in the form of what? Context switching time only. The thread context switching time is lesser than your process context switching time. And the last one, you know, what is that? Thread is under sharing mode, which shares global variables, code, data, address space with other threads. But here, every process has its own the requirements, and its own process control block. Now you see, when I'm talking about a thread, it looks like this is only thread. This thread is under the control of two important concept. What is that? Thread control block. If I am saying the thread 2, this is also another thread. It is also under the control of what? Thread control block. But you see that overall this, please understand friends, these two threads are belongs to one of your process, and your process is under the control of your process control block. Please don't forget that. So whenever I created a threads, then the process is not going to run. Please understand, this entire process is not going to run. This time the process is going to run in the form of what? Smaller threads. So therefore you see that these threads are under the control of TCB, and this process under the control of what? Your PCB. And now we have got two important threads. One thread which are executing in kernel mode, they are called as a what? Kernel threads, kernel level threads. And the other threads are user level threads. So what is a user level threads? User level threads are being created by user program, and kernel level threads are being created by kernel program, nothing but system softwares. What are the differences? Very important differences I will tell you. Observe carefully. One point is kernel level threads are executed in kernel. User level threads are executed in user. But kernel do not know about the user level threads. Please understand. Kernel do not know about what there are any user level threads or not. Kernel doesn't mind because all user level threads are executed on this particular user space only, and this is your kernel space. And the next one is that kernel level threads are mainly which requires a kernel support and which requires a hardware support. Without hardware support, kernel level threads cannot be run, and there is a proper system calls required in order to do that kernel level threads. If at all one particular kernel level thread is blocked, then remaining threads are going to work on its own. But whereas user level thread, if at all any thread is blocked, then entire user level threads, all threads are going to be blocked. But this can be avoided in kernel level thread. What is that? If any one thread is blocked, then other threads are doing it their own work. They are not going to be blocked. This is the concept. So these are the three important points. What are that? Management is done in a kernel space, and here management is done in user space. And the next point is, if one user level thread, this is important, another important point. If one user level thread performing blocking system call, then entire process will be blocked. But in kernel level thread, this is the different issue, because every kernel level thread I can say that it is act like a process only, which is going to run on a different particular environment, such that the other threads are not going to be under blocking. So it does not require any system calls, but kernel level threads require a separate system calls, and this requires hardware support, and these are not required any kind of hardware support. No hardware support here. And you see, user level threads are having a less context switching time than your kernel level threads. And one more, your threads context switching time, your threads context switching time is lesser than your process context switching time. I'm talking about like this, but here also you have the comparison. User level threads context switching time is lesser than kernel level threads context switching time, because kernel level threads are somewhat heavyweight than your user level threads. User level threads are the main ultimate lightweight applications. So therefore, it requires more context. This requires less context. So it is done in user space using a thread control block. It is also running in thread control block, which is running in kernel area. Now, what are the user level threads and what are the kernel level threads? These are kernel level threads like Windows and Solaris operating system, which are using the concept of a multi-threading concept. So they are meant for kernel level threads, and your Java multi-threading concept is implementing using a what? User level threads. So user level threads, you talk that it is a Java threads only. So evening we will see some theoretical questions on this threading concept and fork concept. But the question is given on a deadlock concept in this, that we will look at it. It's a 1 mark weightage fork and threads together. So this is a multi-threading model. What is a multi-threading model? Please understand. Every thread has stack, and every thread has program counter, and every thread has register. So if you are having one more thread onto that. If you are having a one more thread onto that thread within a thread, now what is going to happen? It is been completely overlapped once again. You have the concept of what once again stack here, and you have other kinds of resources which is overlapped onto this. That's the concept. Now we have thread life cycle. However, we have process life cycle. We also have thread life cycle. What is that? Threads are created using a new. What is the function call we use? Create call we use to create the threads. Threads are being started. That means they are running, which is given to your corresponding CPU. And threads can be sometime under sleep. Sleeping is nothing but they are under waiting. So whenever they are under waiting, they simply send back to your secondary memory. And now you see, whenever there is a concept of a deadlock, the threads are going to be under blocked. If at all thread completed successfully, the threads are what? Terminated. Once threads are terminated and its stack is reclaimed. And its stack is what? Reclaimed. So whenever threads are joining, then all your threads are supposed to be under waiting. So we are using a concept of what? Joining. So whenever you are joining the threads, then you have to wait each other for some time. This is how about your thread life cycle. So there are different kinds of user level threads. They are many to one and one to one and many to many. Please understand, right now we are using this. Currently running threads are 1:1 because it is going to give you high concurrency. High concurrency you are going to get only through 1-to-1 threads only. So 1-to-1 threads are most suitable for parallelization or multiprocessing system. So what is the meaning of that? Let us see. So what is the meaning of this? All these user level thread models can able to map to your kernel level thread. So how it is going to be executed, we will see here. When I am talking a many to one, so what is a many to one means? Please understand. Many user level threads. These are user level threads. There are many user level threads. There are 3 threads I am running. They are under the control of TCP and they are being communicated with, please understand, they are being communicated with one kernel level thread. That is the concept of how many to one is being done. Please understand, many user level threads are mapped with one kernel level thread. What is the meaning of one kernel? Please understand. I have many user process, but I have got only one CPU. Please understand. I have got only one CPU. Therefore, how many threads you can run at a time? Only one thread you can run at a time because I don't have multiple processors. When you have the multiple processors, then you talk about the threading concept and fork concept. Otherwise, don't talk about this. So I'm having a thread. That means what a program is divided into. A program is divided into multi-threading concept. So many user processes. That means what here process is nothing but please understand as a thread. So I have got many user level threads are there. Then they are going to be mapped onto only single process. That single process is nothing but I have got only what? One kernel only. So this is more suitable whenever you don't have multiple CPUs. That's the problem. What is that? So one too many. All user level threads are mapped onto your kernel level thread. This is only implemented when you have got only one kernel. When you have got only one kernel thread, then you can able to use the many to one concept. What is the problem? If any thread issues a block system call, if this thread issues a block system call, then automatically, as I am using a single level thread, then automatically other threads automatically they are under what? blocking only. It is not that much so effective because you are accessing only single kernel thread from your many of your user level threads. So this problem can be avoided in 1:1 thread concept. So what is the advantages? What are the disadvantages? We will see. So this M is to 1, I'm talking about M is to 1. This M is to 1 is only when operating system doesn't support multi-threading concept. When you don't have multi-threading concept, then you're supposed to use the concept of what? M is to 1. What is the M is to 1? N threads from 1 to N. N threads are located to your single kernel only, as I created only one single thread because I'm having the concept of what? Single CPU. So this problem can be avoided. What is the problem? The problem is that only one thread can run in the kernel. So therefore there is no concept of parallelization. Please see, there is no concept of what? Parallelization. This problem can be avoided using the concept of what? One-to-one thread. What is a one-to-one thread? Now you see, earlier I shown that I have got three threads, thread 1 and thread 2 and thread 3. Now you see, I am able to run three threads in the sense I am able to have three kernels. Kernel thread 1, kernel 2 and kernel 3. You can have many kernels, but you see that minimum you require three kernels because as you are sending three threads. So this will be given to this and this will be given to this and this will be given to this. Further, this thread will communicate with a single CPU 1. This thread will communicate with single CPU another CPU. This thread will communicate with another CPU. So three user level threads are being communicated on three different kernel level threads. This is the concept of 1:1. So much more we are using a 1:1 threads right now in your real time cases. Now you see, so each user level thread executes on separate kernel level thread. So there is a requirement of what? M or N kernel level threads in order to run M or N user level threads. What is the advantage? More concurrency. If this, please listen, if this gives a block system call, if thread 1 gives a block system call, then what will happen? This CPU is going to be under block. Please understand, as you are corresponding to this kernel only. But this thread can run. They are not going to be under block. They are not blocked because they are running on to different kernel level threads. That's a very, very important point. What is that? If any thread, if any thread issues a block system call, then other threads are not going to be blocked. Please understand. It allows other threads to run when a thread makes a block system call. It's unlike to your many to one concept. Therefore, you see that multiprocessor architecture you can able to utilize well. So real-time application, I said that 1:1 we are using in Windows operating system and IBM OS by 2. IBM is also following this kind of 1:1 threads concept. This is a very, very important point. Right now we are working with 1:1 threads only. But what is the problem? The problem is only one. N user level threads need N kernel level threads. So you're supposed to have N kernel level threads in order to run your N user level threads. So that's one of the disadvantages. Now you see there are 1, 2, 3 threads are there and each thread is associated with one kernel level thread. Come to the last model, that is many to many. What is a many to many? Any thread can be assigned to any CPU. Please understand. I have got multiple threads of process 1. Please understand. I have got another process which consists of multiple threads. I have got one more process which consists of many threads. I am talking about user level threads. They can be mapped onto your kernel level threads, many kernel level threads. So now you see they can be allocated anywhere. So I have kernel level thread and kernel level thread. See that. So therefore what is happening? I can switch over anywhere to anywhere. I can switch over anywhere to anywhere because I am having MS2N concept. It is also called as hybrid multi-threading. So whenever you are having MS2M concept, it is a what? Hybrid multi-threading. So this is the architecture of this. What is the architecture? I am having multiple threads, multiple user level threads. If I am having, these are your multiple user level threads. They are being assigning on to multiple kernel level threads. This is the point. Now, any doubt you can ask me. This is the end of your thread concept. So we learned what is the difference between fork and thread. What is the difference between fork and thread? Both are for parallelization only, for effective utilization of multiple CPUs. But fork is going to give you duplicate output, and time complexity also it takes same. That problem can be avoided in thread because the thread is a part of your process, very small piece of code executed in threads. Threads are very faster than your normal processes because a thread is a lightweight which doesn't have much resources, minimal resources it has got. So that's what. So we have two different varieties of threads, user level threads and kernel level threads. User level threads are much more lighter than your kernel level threads, and kernel level threads require hardware support and user level threads not require any hardware support. So user level threads doesn't require any system call separately because thread management is done by thread control block only. But kernel level threads requires what? A system call, because to want to create a kernel level thread, please understand, you want to create a kernel level thread, there is a what? A separate system call is required. Then only you can able to create a what? Kernel level threads. But user level threads are done by your thread control block only. And I have told you another point is that all the threads are looking by your TCB, thread control block, which is very similar to your process control block. Okay friends, the questionnaire we do on evening class, that is 7 p.m. to 8 p.m. We will do the questionnaire. Around 16 questions are there. Some are given in the previous examination, some are prepared by me. We will discuss those questions in the evening class. Don't miss, because if you have any doubt in this video, that doubts can be cleared in the evening session, because some of the very important tricky questions only I found. So using by solving those questions, you will understand the complete concept of your threads and fork statement. Okay, so we will meet evening class, that is 7 to 8 p.m. on Unacademy student learning app. And tomorrow we have the concept of what? Tomorrow session I'm going to start a deadlock. So don't miss deadlock. I need your presence from starting to ending deadlock concept. Tomorrow we will discuss off part of the deadlock, that is the deadlock characteristics, deadlock and deadlock preventions. Day after tomorrow we will discuss about banker's algorithm. But tomorrow we will learn about, we will go slowly, what is the deadlock characteristics, how deadlocks are formed, how deadlocks are going to be preempted. So tomorrow our class on YouTube is as usually 2 to 3, and evening special class is as usually 7 to 8. We'll meet tomorrow. Thank you. So all of you, please understand, follow thread concept. Again, you will get the same concept in the evening. Don't miss 7 to 8 p.m. special class. If at all you have got any doubt in that question, so I will explain that answer through concept once again. So again you will get what benefited using that theoretical concept. I hope so you got understood why do we require a threading concept, why do we require a fork concept. But naturally some people, some operating system prefer fork, some operating system prefer threads. Especially Linux operating system follows forks more, and Windows operating system follows what? Threads more. So these are the different varieties. But you please confident. Right now we are using a 1:1 threads in a real-time operating system like IBM operating system 2 and Windows operating system and many other Solaris operating systems also. So if anybody asks you which is the real-time threading we are using, 1:1 threading, that is the easy way to construct your threads. Okay, meet in the evening session and tomorrow deadlock session. Thank you to all of you.